Okay, hello and welcome everyone. We are very glad that after the delicious lunch you have made it and you have made it to our talk. We are going to tell you about advanced visualization of Spark and in fact also Fling jobs. This is a finding that we have been developed recently, and practically the motivation was that somehow we needed to know more about our production topologies, and that's what led to this project. So let's see the outline, how we are going to address this today. So basically, we are going to give you a brief introduction, and then the motivation and the challenges that we are facing. We will tell you about the current visualization in Apache Spark, and also for that matter, Flink later. We will also tell you that the basic challenge that we were facing, other than not having the right metrics to actually debug our applications, was rooted in data skew, and we needed to tackle that. After we have promised you in the abstract and also at the blog post that we did with Hortonworks after winning the Community Choice Award, that we are going to extend the visualizer to another data processing system, namely Flink. And of course, this is something that we would like to present to you. And then we are concluding our talk with some future plans. Okay, so a little background on us. We come from the Hungarian Academy of Sciences, which is basically a research institute, but we also have very strong industry ties. But that means that it's very usual for us that we actually get use cases for example, the telecommunication sector. And actually, this was motivated by a use case with Ericsson Hungary, where we had really large amounts of data, gigabytes per second flowing in, but at the same time, the distribution was a real challenge. So we had this application with Ericsson. Basically, the setup was the following. We had some data of the telecommunication network, your mobile phones communicating with the telco towers, and we needed to do some basic aggregations on that. So when we were developing the aggregation and we deployed it on test data, everything looked fine. We have looked at all the health metrics and it seemed okay. But then we deployed it against the real data set, and despite the fact that we've seen that everything should be running fine, things got really slow, or they could even crash. So we were just scratching our heads with Zoltan and needed to find out what did go wrong. And there were a couple of catches that we needed to address. If you look at the current UIs in most of the systems, usually they will tell you about the logical plan of a job. We are going to show you a couple of figures about that, but basically it only breaks down to the operator level, and you don't really know information about the physical level of your job, and basically that hindered us from developing an efficient solution. And the reason behind was the following. Usually you are dealing with power law distributions, and some of these use cases, what you see is you have a couple of really heavy keys in the key distribution, aka we are going to call it for whatever reason the Bieber effect here. So practically if you were to do a grouping on Twitter by the count of followers, if a machine receives this entity called Bieber for whatever reason, it's going to have a much larger job than all the others. And this is practically that we would like to address distributions that look approximately like this, name it Pareto, name it Power law, but practically that was the root of our pains. Of course, by default, if you do a group by on these kind of things, and usually that's the case when you do aggregations, basically you do hash these into random buckets when you look at the physical plan, and just in those buckets you actually apply the aggregations. And of course we can do better than that. Actually, there's a nice probabilistic algorithm to deal with this problem, mostly developed by Zoltan.
Okay. Thank you, Martin. So before we jump into our problem and into the solution, let me recap the aims and the goals that we would like to accomplish here. So our first priority should be to handle the data skew somehow, because as Marta mentioned, we found out that most of our telecommunication data processing workloads suffer from these inefficient communication patterns, usually introduced by, of course, data skew and the shuffle behind the data skew. And we also would like to help our developers. We wanted to help our developers to be able to write better applications by detecting the issues of the logical plan, but not only the logical plan, the physical plan, which is usually missing or hidden from us completely. We also wanted to help our newcomers, our brothers and the community, to understand the usually quite difficult concept of the data processing systems. We wanted to help them to learn much faster. And we also wanted to build and create a tool that would allow us to demonstrate and guide the testing of our new solutions, like adaptive repartitioning techniques and so on. So before we go any further, let's take a deep dive into the execution model. Okay, we are not going to go into too deep, but we have a very important thing to remember here. So Spark is basically, of course, an extended MapReduce model. And the key thing is that here that a previous stage has to complete all its tasks, right, before the next stage, or tasks from the next stage can be scheduled. This is something that we usually call a global synchronization. And this is usually called the shuffle phase as well. As you see on the right-hand picture, even when we usually have an even partitioning in some stage, what can happen is that when you have some group by that Martin has mentioned, or some other operation like join, in which you would not like to, or you are not able to do a map sign combine, then after the shuffle phase, based on your operation and based on your data distribution, what can happen is that you are going to have slow tasks because most of the Bebers or Madonnas or whatnot are going to go to the same task, right? So data skew can introduce slow tasks. And this is something that we have examined thoroughly. So the other problem is that in most cases, the data distribution is not known in advance. The data distribution can change, of course. We have batch and streaming workloads as well. We have streaming use cases as well. And in these cases, usually concept drifts are very common, right? Data can change. In some other time, a Bieber is a very prominent key, but some other time, Madonna is the star. So we need to deal with the concept drifts. Okay, so for that matter, we wanted to first understand the physical plan. And understanding the physical plan has or can lead to designing a better application, as we found out. It can help us to uncover bottlenecks that are really hard to identify otherwise. It helped us to pick the right tool, right system, right data distribution system, or right API for the job that we have at hand. And we have also found out, as I've mentioned before, that it can be quite difficult for newcomers to understand. And we wanted to help ourselves by gaining insights to new adaptive strategies like on-the-fly partitioning and optimization mechanisms. Okay, so first we wanted to build a visualization tool. And before that, we have examined the current visualization tools, and we have found that, unfortunately, these tools and the metrics behind the tools are missing the fine-grained input and output metrics, which are not available in most systems, like, for example, Spark. And these visualization tools also does not capture the data characteristics, because on the first hand, we would like to make our applications or our system to be data aware. And usually this is very hard to accomplish, because there you need to have a lightweight and an efficient solution, because we don't want to do less by trying to do more, right? We don't want to put too much overhead to the system that we are trying to use, in this case, Spark. And also, we have found out that most of these visualization tools are not able to visualize a physical plan. For example, of course, we have a very nice visualization in Spark by default, which can help you to better understand the plan created by the DAX scheduler. But we wanted to do more than that. So, to have more than that, you need to collect information during the execution that is otherwise not available, right? Like, for example, in Spark. So we know that we have the so-called shuffle phase or global synchronization, and during this, the reducers on the next stage are going to pull their partitions in the form of these so-called shuffle block fetches. And here we can distinguish local or remote block fetches. And this is a nice example of these local block fetch infos. On the right-hand side, we also wanted to collect the data characteristics on both the task input and the output, because these are the two paths that we have. Of course, the shuffle write and the read. But we have used the shuffle write metrics extensively in our optimization strategies. And this is an example of such a data characteristics. On the left side, you can see the keys, and on the right side, you see the frequencies that are being or has been approximated for that key. Okay, now we can ask that, okay, how do we approximate the frequencies? For that, of course, as we've mentioned, you need to have a scalable sampling. So the key or the goal here is to somehow approximate the key distribution with a nice strategy that is not going to be sensitive to early or late arriving Webers, right? Because there, let's say if we have a streaming solution then, or use case, we need to prepare for these so-called concept drifts that can happen. It also needs to be lightweight and efficient, because we don't want to put too much overhead to our system. And also, it needs to be scalable. And by scalable, we mean that, okay, it needs to be prepared that the data volume can be very, very huge. And for that matter, we have employed a very nice backup strategy. Of course, the solution or scalable sampling is a huge implementation and a huge improvement. I'm not going to go into too much details, but I'm going to go through the basics of this sampling. So let's see. First, we are going to have something like a histogram. We are going to store keys, and we are going to approximate the frequencies of the keys in these so-called counters. And then, because we have a probabilistic sampling here, we are going to initialize a sampling rate. It is going to be 1.0 in the first place. And this is going to mean that, okay, I'm going to record each key. So I'm going to update the counter for each key whenever I throw the dice and I find that I'm under the sampling rate. So if that happens, I'm going to increase the corresponding keys counter, right? Okay, so the other thing is that because we would like to handle the data skew, we are not considered about all the trashy keys. Okay, we are just considered about the prominent keys, the Webers, and the heavily loaded cells, for that matter, if we are in a telecommunication use case. So for that, if we see that we would like to add, or we would add too much counter, what we're going to do is that if we see that we would add the counter over a light boundary, we are going to use our backup strategy, and with a multiplicative factor, we are going to reduce the frequencies, each frequency, and then with the same factor, we are going to reduce the sampling rate as well. Okay, then what can happen is that, okay, new counters are going to arrive in, but if we pass a hard boundary, we are going to truncate the whole histogram, and then we are going to utilize our same backup strategy to reduce the frequencies, and then we are going to reduce the sampling rate as well. This is very similar to something called reservoir sampling, but we wanted to have more sophisticated solution for this use case. So now that we have all the information collected, we need to make it, of course, available somehow. For that matter, Spark has a very nice REST API, and we have enhanced the Spark REST API to provide all the block fetch infos, all the data characteristics information of tasks. And we have also created new queries, like you can ask something like, okay, what happened in the last 3 seconds, and you are going to have a bunch of new events coming at you. This is something that the visualization actually does. And this is a very nice example how such a query looks like. It aligns perfectly with the current Spark REST API. So now we have arrived to actually check the visualization and how it looks, how it moves, and what features do we already have. So most of you have probably seen pictures like this, right, when you were reading about Spark, which describes perfectly how narrow dependencies and wide dependencies work with all the different pair RDD operators. So what you're going to see here is that, okay, what happens when these pictures come alive? Okay, so this is the fairly nice UI of the visualization, as you can see it on the video. So what we are doing here is that we are polling the REST API, task events are coming at us, and we are going to put the task out, and we are going to group them into stages. And of course, when the shuffle part happens, we are going to have all the different edges which represent the communication between the tasks. And then, of course, we have a nice feature that you can consider only the local, or you can consider remote edges. Of course, you can have a lot of information out of tasks, like you can say, okay, what operators have been pipelined, and you can, of course, also see the data distribution, if you will, and so on. So in our fork, this solution is currently available in the Spark. So all you need to do is just pick your favorite job you would like to visualize. You are going to go into the job tab. You will click on the job, and you will find the execution visualization right under the original DAG visualization. So we have used this tool extensively to discover issues in our deployments, and also we have used it to test our new repartitioning strategy. I'm going to show you a few pictures about this very shortly. Now, so let's get back to our first priority, right? Our first priority was to tackle the data skew somehow. And here, our goal is basically to use all the collected information to handle the data skew dynamically and on the fly. So by dynamically and on the fly, we mean that we don't want to pre-sample the data. We don't want to have a subset of the data. We don't want to run the job offline and then be smart about it later when we rerun the job. So what we are going to have here is that all you need to do is just switch one lever on, and then you are going to have dynamic repartitioning on, and then it is going to capture your data characteristics, the characteristics of your data, and if it's necessary, it is going to repartition the data on the fly. So you're not going to need to do anything, any hint. Basically, it is going to deal with it. And we wanted to use this solution both in our batch and streaming use cases. So currently, we are working on the streaming part right now, but we want to enable this feature to work on any of the Spark's API. So I'm not going to go into too much detail because we don't have the time, but one thing that is necessary to mention is that we currently have a paper in progress. It is going to come out in the next 1 or 2 months, right? And There's going to be more technical talk in the next Spark Summit, so if you're interested, come and find us. So let's see an example. Let's say that you don't have this dynamic repartitioning module or feature switched on, and you see that, okay, in some specific stage, I'm going to have very prominent keys that is going to basically slow down some or most of my tasks, so that I identify that, okay, I have heavy keys, and these heavy keys are going to create heavy partitions, which are going to introduce slow tasks. So what I do is that when I switch on dynamic repartitioning, I'm going to see that I have sent all the Bieber's, all the Madonnas, and all the big stars into different tasks, different partitions exclusively. So all the trashy keys are basically sent into some other partitions. And by this, I was able to minimize the size of the biggest partitions. Practically for us, as Marta mentioned, because we have these distributions, so-called Pareto distributions, these distributions are very common. For us, this means that we were able to speed up our jobs by a factor of 2 on an average case. But there can be some rare cases when it goes up to by a factor of 5 or 6. So it is a very efficient solution.
So after digging deep into how to deal with data skew and how to get it running on Spark, we have also extended the solution to other data processing engines, because the point that we would like to make is basically all these engines that rely on a DAG can be visualized in such a manner. So one thing that you will hear for Flink and Spark folks is that the underlying engine has its differences. And the question is whether for this visualization and for the repartitioning for that matter, is that relevant, or are we actually on such a low level in the network and the shuffling phase that it doesn't matter anymore and that we can actually reuse the same logic? And fortunately for us, the case is the second one. So I had to add some minimal code, a couple hundred lines of code to the current Flink metrics so that I could collect the same metrics that Zoltan did for Spark. And then I also exposed it via the Flink REST API. And currently it's available on the job manager. Also, it's just on my fork, but I would like to push it into the main Flink code base. And of course, we had to map the two models. So I would like to have a look at the two execution models and see whether they are really that different. So if you look at, of course, Zoltan has already showed you some explanation about how Spark works. Basically, if you look at the batch mode, it runs the computation in so-called mini batches, and then we have this global shuffle phase, which means that nothing runs from here, from B, before A finishes. And that's something that we know from the history of databases, if you wish, that in a lot of cases, pipelining can yield you some benefit, and that's what the Flink engine relies on. Practically in the Flink engine, whenever this operator is ready with some computation, it's going to forward it to the subsequent operator or a parallel instance of the subsequent operator. And so it's slightly different in that regard, and they might be more efficient in such cases. One of the nice things that we also wanted to demonstrate with this setup is actually you don't really have to change your architecture when it comes to switching from batch to streaming for the Flink engine, but you have to do something that is a little bit different when it comes to Spark, the mini-batching solutions. So we decided to bring this visualizer that was implemented for Spark batch at first to Flink streaming to show you the two ends of the spectrum, that you can actually go really far with these metrics and this solution. So let's have a look at the currently available visualizer also in Flink. As Zoltan has already showed you, practically the Spark one gives you a logical plan. And I can say the same for the Flink visualizer, and that you can see the operators. This is a timely window join. We have some sources, we do some mapping on them, and do a window join based on that. But we don't really see the physical information, the information that we would need to actually debug the kind of challenges that we have been facing in this specific motivation use case. So how do we deal with that? Of course, after extracting the right metrics and exposing them to the already available Flink REST API, I managed to set up the same use case for Flink. Here you see a job that has been running on 4 physical machines, hence the colors. Each machine was running 2 instances of the operators, and I think this is actually a word count type of program which has a windowing component in the middle. But practically the point is that, yes, we were able to make the visualization pluggable and make it run not just on Spark, but also on Flink. So let's speak a little bit about our future plans and how to advance with this project. Of course, one of the main goals is that you also would be able to try out this visualization and give us feedback, so we would like to open source it, and we are very looking forward to the use cases that you find it useful for. Zoltan has already mentioned that a paper is progress on the more researchy part. We have received some valuable input from both the Spark and the Flink community that, for example, collapsing some parts of the whole topology would be really useful, because usually you have these huge topologies where showing everything doesn't really show anything anymore. Of course, any requested visual improvements or features would be very welcome, so that's why we would like to open source it, so you can suggest those or even implement it yourself and contribute it back. And as we have already outlined it, these metrics are not yet in the official Flink or Spark code bases, so we would like to contribute them back so you can run it against the official version of the code bases. And actually in the Flink case, there's a Jira that we are blocked by, but hopefully it will be solved in the very near future. So, some conclusions of the talk. When it comes to big data, usually the devil is in the details. The really small things can hinder your job, very inefficient. And adding the right visualization tool might seem a big effort, but actually it helps you a lot in the long run. And I think, or we think, that the community should maybe put a little more emphasis on building these tools. In the special case of data skew, we have managed to actually tackle the challenges and come up with a nice repartitioning strategy, which can be surprisingly efficient. So thank you very much for your attention, and we would love to receive some questions. Yes, please.
The deeper effect you mentioned, skew, is that per cell, individual cells going on? So usually telecommunications data is looking at quality of Beaver objects on the cell network.
Yeah, so the question was, let's make a connection between our telecommunication use case and this celeb figure that we have been using as Bieber and Madonna. When we see these kind of events in the telco use cases, usually when we group by the cell tower, so we would like to eventually form a heat map of, for example, the download speed of the users, the experience of the users, and whenever you have a football match, that's Bieber, if you wish. Well, if no other questions, then thank you very much for your attention. And of course, we will be available through the conference. Don't hesitate to contact us.